Quick release hooks and bollards are specialized devices used in ship mooring operation to ensure the safe and efficient securing and releasing of mooring lines. They play a critical role in enhancing safety, operational efficiency, and flexibility during the mooring and unmooring processes. Now let us look at the purpose of quick release hooks. Quick release hooks allows for the rapid disconnections of mooring lines in emergency situations such as sudden change in weather, equipment failure, or the need for an immediate departure. They enable faster mooring and unmooring operations, reducing port turnaround and times, and improving operational efficiency. These hooks can be easily engaged or disengaged, making them suitable for various mooring configurations and vessel types. Designing a holding down bolts for a quick release hook involves considering structural loads, material properties, installation methods, and safety factors. Some of the design requirements that need to be identified are the load capacity, that is, to determine the maximum static and dynamic forces acting on the quick release hook. The bolt type. The designer need to choose between anchor bolts, either cast in place or post-install bolts, which has expansion and chemical anchors. Similarly, the bolt size and material need to be determined, and the bolt need to be selected based on the strength, corrosion resistance, and fatigue performance. Other factors for consideration are the environmental factors such as exposure to corrosion, temperature changes, and vibrations. This part of the video is about how we design the holding down bolts. Some of the design assumptions are as follows. For the holding down bolts, the material tensile strength is 415 MPa, yield strength 240 MPa, elongations 30% is the minimum value. Next, we need to know what is the allowable stress for bolts. In accordance with Australian Standards 1250, the maximum stress for structural holding down bolts are as follows. The shear stress FB equal to 0.33 Fy, that is equivalent to 79.2 MPa. The tensile stress FAT equal to 0.6 Fy, equivalent to 144 MPa. We need to use the interaction formula for the combined shear and tension, where the FB divided by the capital FB to the power of 2 plus FAT divided by the capital FAT to the power of 2 should not be more than 1, where FV and FAT are the calculated shear and tensile stress respectively. Capital FB and F are the maximum permissible stress. The other assumptions are the allowable stresses for concrete. Here we assume the minimum compressive strength for concrete to be 30 MPa, maximum permissible bearing stress of 12 MPa, maximum permissible shear stress of 4.4 MPa. For cast-in bolts, effective length for bearing stress rising from shear force on bolts is 600 millimeter. We're going to look at a sample calculation, how to design a double 30-ton hook unit. The case, there will be several cases that the designer need to consider, but for this particular video, we're going to just do a sample calculation for one of the case. In this case, we have two hooks fully loaded, with each of them taking force of 30 ton. So the diagram shows the plan view of the force as well as the locations of the 6 bolts. We also have the cross section across the plate that support the quick release hook. The maximum tensile stress occurs in rear bolts due to the overturning moments. It is calculated as overturning moment equal to 60. That is the pull force time 270, which is the lever arm, multiplied by 9800 is a conversion from ton to newtons. So the total overturning moment obtained from this force is 1587 times 10 to the power of 6 Newton millimeter. The maximum bolt tension TC per bolts in kilonewton is equivalent to 158.7 times 10 to the power of 6 times 470 divided by 2 times 270 times 357 plus 2 times 470 times 5.7 times 10 to the power of negative 3. Then we have the TC equal to 104.1 kilonewton. The tensile area for M56 bolt is 2030 millimeters squared. The stress on the bolts due to the force of 104.1 kilonewton is 51.3 MPa. So the stress on the bolts is obtained from the calculations of 104.1 times 10 to the power of 3 divided by the area of the M56 bolts, which is 2030 millimeters squared, which will produce bolt stress of 51.3 MPa. The shear stress is calculated by taking the total shear force, that is 60 ton, and divide by the minimum stress area for shear for M56 bolts, which is equivalent to 2,460 millimeters squared. So the shear stress per bolts is 39.8 MPa. So based on the combined stress interaction formula, we obtain the maximum allowable shear stress FBF equal to 79.2 MPa. Maximum allowable tensile stress is FAT equal to 144 MPa. And using the combined stress interaction formula, we can find that this value is equal to 0.4. Thus, the bolts are considered satisfactory for taking care of the loading